this video, we're going to continue on with Chapter 7. So we're going to be looking at periodic trends. So we will explore atomic radius, we'll talk about the effective nuclear charge and how that is going to affect atomic radius, ionic radius, ionization energy, as well as electron affinity trends on the periodic table. In this lesson, there are a few new vocabulary terms you can see off to the left-hand side, as well as one new equation that we'll be looking at. We'll be looking at properties of atoms on the periodic table, and some of the atomic properties that we're going to be exploring are orbital energy, atomic size, ionization energy, and electron affinity. So orbital energy is the electron stability of the elements. So the more stable the electrons, the lower the energy is going to be. So the closer those electrons are to that positively charged nucleus, the more stable those electrons are. The further away they are from the nucleus, the higher in energy they're going to be. Atomic size. So for atomic size, what we're talking about is the diameter of an atom, and that's including the electron cloud. So we'll look at how to predict electron size based off of where the elements are or the atoms are on the periodic table. We'll also relate that to ionic size as well. So if we have cations or anions, how that changes their diameters. We'll also look at ionization energy. So ionization energy is the energy needed to form positive ions. So in order to form a positive ion, what are we doing? We're removing an electron. So ionization energy is the energy needed to remove an electron. Electron affinity then is going to be the opposite, the energy needed to form negative ions, so anions. So when we form a negative ion, what are we doing? We're adding an electron to the atom. So remember, we can't change the number of protons, so it's only electrons we can change to affect the charge. So electron affinity is the energy needed to add an electron to an atom. So first we're going to look at effective nuclear charge, because this is going to help determine the effects of some of those other atomic properties that we looked at on a previous slide. So effective nuclear charge describes the electron's experiences. So the electron experiences repulsion from other electrons. Because they're all negatively charged, they have the same charge, they're going to repel each other. So due to this repulsion, it cancels out some of the attraction that that electron feels for that positively charged nucleus. So we calculate that by calculating the effective nuclear charge, or Z sub EF, often written as Z with an asterisk. So we take the nuclear charge and we subtract the number of core electrons. So why are we subtracting the number of core electrons? Because those core electrons are getting in the way of that electron we're studying. So we're studying an electron. Any electrons that are in shells closer to the nucleus are going to be shielding or blocking our electron from feeling that positive charge from the nucleus. So we need to subtract that out and indicate that we understand those are sometimes getting in the way and decreasing the effective nuclear charge felt by that electron. So when we're looking at effective nuclear charge on the periodic table, the trend that we see is that it increases when we move from left to right across the periodic table. So what we're saying is, as Z increases, or the effective nuclear charge increases, the electrons feel a strong attractive force from the nucleus. So why is this? Well, the higher the Z is, the Z asterisk is, that means the less core electrons there are, because remember, we're subtracting out the core electrons. So the less core electrons there are, the less electrons are blocking the experience of our electron from feeling that positive charge of the nucleus. So when we see an effective nuclear charge increase, that is in turn going to decrease the energy of the atomic orbitals. Because remember, we decrease the energy of the atomic orbitals when they feel a strong pull towards that positively charged center. because if they feel a strong pull to that positively charged center, they are held more tightly and are thus more stable and harder to remove. So applying this to orbital energy with a depiction. So for instance, if we were looking at this outer electron, this valence electron. So when I talk about valence electrons are the electrons in the outermost shell only. So if you notice in this depiction of an atom, there's only one valence electron on that outer shell. Now all the electrons on any shells inside of that are going to be called core electrons. So you notice there are two core electrons in this depiction of an atom. So the core electrons are held more tightly than the valence electrons. Why? Because those core electrons are closer to that positively charged nucleus, so they feel the attraction of that positively charged nucleus more, causing them to be held tighter. So if they're held tighter, they're harder to pull off, they're lower in energy, they're more stable. The valence electrons, however, in the outermost shell are easier to pick off because they are further away from that positively charged nucleus. And not only that, but when we looked at the effective nuclear charge, remember, we have to subtract out those core electrons. So the effective nuclear charge is going to be lower for the valence electrons because it has those core electrons getting in its way every once in a while. Because remember, those electrons in the core, as well as the valence, are constantly orbiting, constantly moving, right? So if they're constantly moving, they're going to get in the way sometimes. They're going to shield the effect of that valence electron. So when we're looking at orbital energies and the trends that it has on the periodic table, we see orbital energy decrease from left to right and increase as you go down a group. So atomic radius is actually going to follow the same trend as orbital energy. So you can see on the periodic table that we have below, the arrows are going in the same direction, where you're seeing an increase from right to left across, and an increase from top to bottom. So an increase as you go down a group. So why is this? Well, the size of an atom is controlled by the size of its orbitals. So that's why it has the same trends as the orbital energies. So it's decreasing across a period and increasing across, or increasing down a group, excuse me. So it follows the same trends as I said a moment ago as the orbital energies. Why? So why does it follow the same trend? Well, the lower the orbital energy, the tighter the electrons are held, right? So those electrons that are held really tight can really feel that positive charged nucleus and are attracted to that. Those are going to have a smaller radius because they're more attracted to that positively charged nucleus. They can feel it more, so they have a smaller radius. They're tighter. They have a smaller radius due to that higher effective nuclear charge that they feel. And they have a higher effective nuclear charge because they generally have less electrons, core electrons, blocking and shielding the effect they feel from that positively charged nucleus. So in summary, as the effective nuclear charge increases, electrons feel a strong attractive force from the nucleus. And when they feel that strong attractive force, they're going to be held tighter and thus have a smaller radius. Next, we're going to look at ionization energy. So ionization energy was the energy required to move an electron from a gaseous atom. Now this energy is a positive value because energy needs to be absorbed. If you remember from previous chapters, chapters 5 and 6, the positive values were the endothermic, where energy was absorbed. So that's the case happening here. Now the trend for ionization energy is actually opposite the trend for atomic radius and orbital energy. So what I mean by that is we're going to see ionization energy increase as we go across a period instead of decreasing like it did with atomic size, and we're going to see it increase as it goes up a periodic table. up a group. It's also important to note that ionization energy grows each time an electron is removed. So if you're referring to hydrogen, for example, well, bad example because that only has one electron, let's do calcium. So if you're looking at calcium and your neutral calcium and you're moving an electron from it, the ionization energy required to remove that electron is going to be lower than if you're trying to remove a second electron. So why is the case for that? Well, when you remove an electron from an atom, what happens to the other electrons is they're going to feel the charge of that positively charged nucleus a little bit more because there's one less electron taking away from that pull. So since they feel that pull a little bit more, they're going to be held more tightly, which means they're going to be more difficult to take off. So each subsequent electron that you try to remove requires more ionization energy than the last. Now, as I said a moment ago, the ionization energy increases from left to right across a periodic table, and this is due to a smaller radius. And the reason that the radius is smaller as we go across a periodic table is because those electrons are held more tightly. And since they're held more tightly, it takes more energy to pluck them off. Comparing atomic size to ionization energy. So for atomic size, as we said, it decreases as we go to the right. So you can see the tiniest atoms, or the smallest atomic radius atoms, are in this upper right-hand corner of the periodic table. Now we also said that for atomic size it increases as you go down a group. So if you think about it, this actually makes quite a bit of sense. When we talked about quantum numbers, for instance, the quantum numbers increase as we go down a group as well. And remember, those principal quantum number, that value n, that principal quantum number indicates how many shells are around the nucleus. So what we're doing as we go down a group is we're adding more shells. We're adding more orbits, more circles around that atom. So the more circles, the more shells you add, the larger that atom is going to get. So you can see the largest atom on the periodic table is down here in the lower left corner of the periodic table. Now you'll see the opposite trends as we discussed a moment ago with ionization energy. So ionization energy is going to increase as we go to the right instead of decreasing. Now this is because these are where the tinier atoms are. The smaller the atom, the more closely those electrons are going to be held to that nucleus, and the more they're going to feel the pull of those opposite attractions. So since those electrons are more tightly held, they're going to be much, much harder to remove than the atoms that are much larger. So you can see that's why the ionization energy is going to decrease as you go down a group. So the easiest ones to pluck off an electron are going to be the atoms in the lower left-hand corner. Why? Because these atoms are the biggest atoms. So those electrons in their valence shell, in shell 6 or 7, are way far away from that positively charged nucleus. So those electrons can barely feel the pull, so they're really easy to pluck off, meaning their ionization energy is going to be really low. It doesn't take a lot of energy to pull those electrons off of those super large atoms in the lower left-hand corner of the periodic table. So let's try an example and how we would use these trends with actual problems. So we're going to refer to the periodic table and arrange the following elements in order of increasing atomic radius. So we have bromine, selenium, and beryllium. So the first step is to find these three on the periodic table. So I got bromine, selenium, and beryllium. So we want order of increasing. So out of these three, which one is the biggest? Well, remember for atomic radius, it increases as you go down and decreases as you go to the right. So it's basically increasing then as you go to the left. So smallest atoms are going to be in this corner, upper right-hand corner. Largest atoms are going to be in this lower left-hand corner. Okay, so which one of those three is going to be the biggest? or actually we need to start with the smallest because we're going in order of increasing, excuse me. So the smallest out of bromine, selenium, and beryllium, well, the smallest is going to be bromine because it is closest to this upper right-hand corner. So bromine is the smallest. The next smallest then is going to be selenium. Because remember, as we go to the left, the size is increasing, so bromine is definitely smaller than selenium. And selenium and beryllium are as both in the same spot to the left. It's just beryllium is one more down. So since beryllium is one more down, that means it has an extra shell around it, so beryllium is going to be the largest. So it actually already is in order. Bromine being the smallest, then selenium, then beryllium. All right, let's look at another example, this time doing ionization energy. So for ionization energy, it's the opposite trend, and you are not given these trends, you have to remember them. So first step is to find those three elements on the periodic table. So let's see, arsenic is number 33, then we have bromine, and Sb, is that antimony? There's Sb. Okay, so we have the three circled. Now for ionization energy is going to increase as we go from left to right because these are where the smaller atoms are, and they're held way more tightly. Electrons are held more tightly, so they're harder to pick off, and it is going to increase as we go up as well, away from those super large atoms at the bottom left corner. All right, so we're supposed to be going in order of increasing, so we need the one with the lowest ionization energy first. So lowest ionization energy is going to be antimony. Hope that's antimony. Sb. So why is that one the lowest ionization energy? Because it's the closest to this bottom corner, which has the lowest ionization energies. So Sb is the lowest, then arsenic is going to be the next lowest because we're moving up one, and then bromine is going to have the highest ionization energy. So bromine will be the hardest to remove an electron out of those three. Next, we're going to look at electron affinity. So electron affinity is where we are adding an electron, so trying to make an anion to an atom. So when an electron is added to an atom, energy is usually released. Okay, so remember, released would be a negative enthalpy, giving it a negative value. So for the trend for electron affinity, this is going to be the same as ionization energy. We are going increasing as we go up a group and increasing as we go across a period. So since we said it was a negative energy change, when we add an electron to a gaseous atom in a gaseous state is exothermic, excuse me. The larger the negative number, the more stable the ion. And as we said, electron affinity trend is going to follow the same as the ionization energy. So comparing ionization energy versus electron affinity. So for ionization energy, remember we said this was when we are removing an electron from a gaseous atom. So we can see chlorine here. Once we pluck off an electron, it becomes chlorine plus the electron now by itself. And notice that positive ionization energy. So we have a positive energy value indicating that the energy was absorbed and that it is indeed an endothermic reaction. So endothermic process for ionization energy is the take home here. For electron affinity then, this is where we're adding an electron. So notice we have neutral gaseous chlorine plus an electron. So once we add that electron to it, it results in chlorine with a -1 charge. Now notice for this process, it is a negative energy value. So energy is therefore released, indicating that it is an exothermic process. So that's the take home here. Electron affinity is an exothermic process. Ionization would be an endothermic process. So let's do a recap of the trends. As you go up a group, orbital energy and atomic size are going to decrease. So notice orbital energy and atomic size follow the same trend. They decrease as we go up, with the largest atoms in the bottom left-hand corner and the smaller atoms as you go up. Now for ionization energy and electron affinity, they're going to go do the opposite trend. So they're increasing as we go up a group. Now as we go across a group, let's see what happens. So as we go across a group, once again, orbital energy and atomic size are following the same trend, and they are decreasing. So we see the smallest atoms with the lowest orbital energies in this upper right-hand corner of the periodic table. Now for the ionization energy and the electron affinity, they follow the same trend, and they're going to be increasing as we go across. So let's practice. We're going to rank the following atoms in order of decreasing atomic radius. So that means we want the largest ones first and the smallest ones last. Okay, so first we're looking at boron, lithium, and carbon. So we have, oops, kind of crossed it out, but there's boron, there's carbon, and there's lithium. So the nice thing about this example is they are all in the same period. So we just need to know the trend as you go across. So for atomic radius, the trend as you go across is that size is decreasing as you go across the periodic table, with the smallest elements in this upper right-hand corner. So looking at that, that means that the largest of these three atoms is going to be lithium. So lithium is the largest, and we want to go in order of decreasing, so then boron will be next, and then last but not least will be carbon. Now let's do the next example, and I'll use a different color here. We'll use green. We have phosphorus, arsenic, and antimony. So the nice thing about these three is that they're all in the same group. So if you remember the trend for atomic radius, as you go down a group, the atomic size, the radius, is going to increase because we're adding those shells. We're adding more circles essentially onto that atom. So the largest of these three is going to be antimony because that is the furthest down the group. Then it will be arsenic, and then last but not least, phosphorus. So to sum it up, there are the answers for those two. Let's try another example. Now we're going to look at ionization energy and electron affinity. So we're pairing these two together because remember they follow the same trend. So order of increasing. Okay, so we want to start with the one that has the least ionization or the lowest ionization energy, and then end with the one that has the most ionization energy. So let's look at the periodic table and find these guys. We have sulfur, silicon, and sodium. So here's sodium, here's sulfur, and silicon. These are all in the same period as well, so that's nice. So remember, for ionization energy and electron affinity, the trend was that we are increasing as we go across, because it's harder to pluck electrons off of those really, really tiny atoms in this upper right-hand corner. So that means the one with the least, because remember we have to start with the lowest ionization energy because we're supposed to be going in order of increasing according to the question. So the one that has the lowest ionization energy, where it's easiest to pluck off an electron, is going to be sodium. And if you think about it, that actually makes sense because sodium likes to form a +1 charge. So it's easier to take an electron away from there because it wants to form a cation. Whereas when you go over to silicon and sulfur, those generally like to form anions instead. So it's much harder to remove an electron from those. So sodium is going to be the lowest, then silicon, and then sulfur. Good. Let's look at the next one. We have lithium, sodium once again, and potassium. So we're going down a group this time. So remember the trend for ionization energy and electron affinity is going to increase as we go up a group, because the largest atoms are down in this left-hand corner. And those large atoms are really easy to pluck an electron off of because those electrons aren't held very tightly. So it's going to be much harder to pluck off electrons as you move up the group when those atoms get smaller. Okay, so the one that's going to have the least or lowest ionization energy then is going to be potassium because that's the largest of those three atoms. And then it'll be sodium, and then it'll be lithium. So to summarize, here are the answers that we just discussed. Remove some of this so you can see them better. Going from lowest to highest. And these apply for electron affinity as well for ionization energy since they follow the same trend. Continuing with properties, we're going to look at properties of ions now, so charged atoms. So we've only really looked at neutral atoms and how it's affected with electron affinity and ionization energy for when they become ions. But let's look at ionic size, and then we'll talk a little bit about isoelectronic, but we'll delve more into isoelectronic after we discuss electron configuration during in-person lecture. So how does ionic radius change when we do get a cation or an anion? So cations, meaning positively charged atoms, are generally smaller than the parent atom. And remember, cations are generally metals because metals like to lose electrons to become positively charged. So why are cations usually smaller than their parent atom? Well, it's because in order to form a cation, you have to remove an electron. And if you remove an electron, that means the other electrons that are still present are going to feel the pull of that positively charged nucleus even more, making them hug in a little bit tighter and making the radius of that atom now slightly smaller. When we say parent atom, by the way, we're talking about lithium. Neutral lithium would be the parent atom to lithium with a +1 charge. Okay, so that means lithium as the parent atom has a radius of 152, you can see. And then once we remove an electron, the radius now gets smaller down to 78. And there's many more examples here of the other metals, main group metals on the periodic table. Now for anions, how are anions affected? Well, you can guess it's going to be the opposite of cations, right? So anions, meaning negatively charged ions, they're going to be larger than their parent atom. Now remember, anions generally form with nonmetals because nonmetals like to gain electrons. Metals lose, nonmetals like to gain. So since they're gaining more electrons, there's more shielding effects, the effective nuclear charges are going to go down, and the atom size is going to get slightly larger. So if you look at a few of the examples, let's take oxygen. So the parent atom would be neutral oxygen, and notice the size of neutral oxygen is 66. But then when oxygen gets its -2 charge, because that's what it likes to form is a -2 charge to get that full octet, then it's going to get a little bit larger and be 140 in size. So parent atom is smaller than the anion. So let's do some practice with ions and their sizes. So instead of neutral atoms, we're looking at ions. Now, the first step is to find these elements on the periodic table. And then what I want you to do is figure out their size order, ignoring the charges. We can take into the charges at the end. So I got potassium, calcium, what else do we got? Gallium and aluminum. So notice all of these are not in the same group or in the same period. So let's look at what the trends are for atomic radius. So remember, atomic radius is going to increase as we go from right to left across the periodic table, and it is going to increase as we go down the periodic table. So let's figure out which ones are going to be the largest and which ones are going to be the smallest based off of this. So it wants us to go in order of increasing. So let's find the smallest ones first and the largest ones last, since that's how they want the order. So the smallest one out of these four is going to be aluminum, because it is closest to this upper right-hand corner. Next largest after that is going to be gallium. Then the next largest is calcium, and the very largest then is going to be potassium. So the order is aluminum, gallium, calcium, and potassium. Now the nice thing about this is you'll notice cations, we said, are going to be smaller than their parent compound. So if we know what the parent compounds are, it's going to be the same order as the cations as long as they're all cations. So that order will remain the same. Now the second example, B, now the cations need to be taken into account because you'll notice that they're all the same element with different charges. So now is where you need to know that the parent compounds are going to be larger than the cation, because you're removing an electron, causing the atom to become slightly smaller. So if we're going in order of increasing, the largest one is going to be the one with the smallest charge. So manganese with a +2 is going to be the largest ionic radius, and then magnesium 6+ is going to be the smallest. And that means the magnesium 4+ will be in the middle. So here are the answers in the correct order. You can see that manganese with a 2+ is the largest because it has the lowest positive charge on it, indicating the least amount of electrons were removed from it. And then manganese with a 6+ then is going to be the smallest. Looking at isoelectronic series. So what does isoelectronic mean? It's a group of ions that have the same number of electrons. So when we say a group of ions containing the same number of electrons, they do not have to be the same element. We can compare several different elements across the periodic table, several different ions across the periodic table that happen to have the same number of electrons. They would still be referred to as isoelectronic. When we say the same number of electrons, we're talking about core electrons and valence electrons. So we need to take both into account. Now, since they are different elements that we're comparing, these are going to be different ions, they are going to have different number of protons. Atoms that form ions want to become isoelectronic with the nearest noble gas. So we'll see that trend very often, and it'll be more clear on the next slide. So I just said that Elements on the periodic table generally like to form an ion that will make them isoelectronic with a noble gas in the same row. So looking at oxygen, for instance, finding oxygen on the periodic table. So when oxygen forms an ion, what does it usually like to form? It usually likes to form oxygen with a -2 charge, right? All of the nonmetals in group 16 generally like to do that, like to form a -2. So why do they like to form a -2? Well, if you look at it, oxygen and the other elements in group 16, they're only 1, 2 away from the nearest noble gas. So if they can gain 2 electrons, they will then be isoelectronic with the noble gas in the same row as them, in this case, neon. Now let's look at magnesium. So what is magnesium going to do? For magnesium, magnesium is an alkaline earth metal in group 2. So what charge does magnesium usually like to form? Well, the ion that it usually forms is magnesium with a +2 charge, because metals like to lose electrons to become positive. So when it forms that +2 charge, what's happening is it's losing 2 electrons. So if it loses 2 electrons, we're going to go backwards then instead of forward. So if we go backwards 2, right, we go backwards 1, and that gets us to sodium. Now if we go backwards 1 more, we got to go all the way up into group 2p, where neon is. So now we went back 2. One spot brings us to sodium, the second spot brings us to neon. The reason we're going back 2 is because we're forming a +2. So magnesium is going to be isoelectronic with neon as well. So why is magnesium isoelectronic with neon and not argon? Because if you look at it, argon's in the same row as magnesium. Well, look at it this way. Magnesium has a choice. It can lose 2 electrons to get to neon, or it can gain 1, 2, 3, 4, 5, 6 electrons to be isoelectronic with argon. Losing 2 electrons is going to be way easier than gaining 6. So it goes through the path of least resistance, and that's why it goes up to neon. So you want to find the closest noble gas. So the metals, their closest noble gas is in the row above them. The nonmetals, their closest noble gas is in the same row. All right, so let's try the next one, looking at lithium. So lithium is a metal. So since it's a metal, you know it's going to be isoelectronic with the noble gas in the row above it, as we just said. So lithium's right here, number 3. Lithium likes to form a +1 charge since it's an alkali metal in group 1. So that means it loses 1 electron to become isoelectronic with the noble gas in the row above it, which is helium in this case. Next we have nitrogen. So nitrogen is a non-metal, so it's going to most likely be isoelectronic with the noble gas in the same row. So it has a choice. It can lose 5 electrons or it can gain 3. Now, most often than not, it likes to gain the 3 to form a -3 charge. And when it gains those 3 electrons, it moves over 3 technically and is now isoelectronic with neon, the noble gas in the same row as nitrogen. Rubidium is our last example. Rubidium is an alkali metal, just like lithium was. So rubidium is in period 5. It likes to form a +1 charge. Since it's an alkali metal, losing 1 electron. So rubidium is going to be isoelectronic with the noble gas in the row above it. So since rubidium's in row 5, period 5, it's going to be isoelectronic with the noble gas in period 4. The noble gas in period 4 is krypton. So your answer would be rubidium likes to form a +1 isoelectronic with krypton.